unlike Krita, it doesn't save your drawings.
But you do have the option of taking a screenshot. So if I do anything which has a lot of drawing, I'll take a screenshot before clearing it. Or if I remember, I will, at least. Good. Okay. So I'm going to try my best to cram the best parts of an entire course on matrices, or really linear algebra, into 4 sessions. So we'll see how well I can do. It might be a bit fast, and I'll have to be a bit sketchy on proof sometimes, but I think it should be fun because it's less abstract, so it'll be a nice change of pace from the limit stuff. So what are we going to do today for the first introduction to this? Since our goal is to understand matrices, I should give you a sentence that tells you what a matrix is, but they're going to be 3 kind of bolded words that we haven't defined properly yet. So our goal for the first meeting or so will really be to understand some of these words. So an m by n matrix is something which represents something called a linear transformation from one vector space into another vector space. So m and n label the numbers of rows and columns. So in this first meeting, we're mostly going to discuss 2 by 2 matrices. So there's 2 rows and 2 columns, so we write this as 2 by 2. So by this sentence, we expect that this 2 by 2 matrix should represent some linear transformation from a 2-dimensional vector space into another 2-dimensional vector space. But of course, right now that sentence is formally meaningless because I haven't told you what a linear transformation is or what a vector space is. So the first thing we'll need to do, which will occupy most of our time for this session, is to understand what a linear transformation is. So just a quick roadmap of where we're going today. There'll be 4 main goals. So I'll tell you what a linear transformation is, and by the end of the meeting, hopefully you'll be able to identify, given a function, whether it is a linear transformation or not. So that's one thing. Then we're going to we'll figure out that to get interesting linear transformations, we'll need to go up in dimension. So we're going to go to 2-dimensional space called R2. So then I'll have to show you what are vectors, which are elements of a vector space, what are vectors in R2, and you'll learn how to add and multiply them, both symbolically via algebra and geometrically with a picture. Then we'll learn what a matrix really is. So a 2 by 2 matrix encodes a linear transformation, as we said above, which is something that'll take one of these vectors we'll learn about into another. So it's just a kind of function. It takes an input and gives you an output, but now the input and output are these more complicated objects called vectors. And then the last thing will be to understand what is matrix multiplication doing. So if a matrix is a kind of function, a linear transformation, multiplying matrices we'll see is a lot like composing functions. So we know that you can take 2 functions f and g and compose them to get some f of g of x. So we'll see that matrix multiplication, if m and n, capital M and capital N, are matrices, we'll see that the product m times n of 2 matrices is really doing something like composing 2 functions. So there's some input, and you're going to compose them. And the most interesting thing we'll learn, and this is really the root of why matrices are so important in physics, is that once we see this, we'll learn that matrix multiplication does not commute. You are used to real numbers like x and y, where it's always true that x times y equals y times x. The order is irrelevant. But as I've said, matrix multiplication is function composition. And as you know, if you take 2 functions and compose them, the order matters. If you take the output of g and plug it into f, that's almost never the same as taking the output of f and plugging it into g. So multiplying matrices in different orders will give you a different answer, as we'll see explicitly. And that's really the key. That's very important. And this is really this is what's going to bring us into quantum mechanics. So this is a rapid overview, a roadmap, so to speak. So what are your first impressions or thoughts upon seeing the plan?
Not really comment on the plan, but at first I thought that matrices was, well, just a different way of storing data.
Yeah, I think that's often the way that it's taught in like an Algebra 2 class. You said you didn't cover it in your class at all, so just for my personal edification, what exposure have you had to matrices so far? Where have you seen them, if at all?
I've had none.
Okay, Logan?
Basically, I saw in a textbook a thing about adding matrices. That is literally it. I didn't even do it.
Okay, that makes
See,
sense.
I always assumed that matrices were more able to be equated to something like an array in C++ while coding. So I'm not sure if I'm close or completely off.
That's fair. I think it's useful to separate the representation of a function from what the function is actually doing. So I agree that a matrix can be represented as a square array of numbers. So from a programming perspective, you could think of this, say, in Python as a list of lists, right? It's a list of a two-length list, each of whose elements are also lists of length 2. That's fine. But that doesn't tell you anything kind of at a deeper level about what this thing is supposed to be doing, right? So from the modern perspective of matrix theory, you think of a matrix not just as the array of numbers. You think of it as a specific function which can be represented by an array of numbers. But you can, I mean, if you change your coordinates, for instance, if you're in the plane and you have, say, the x-axis and the y-axis, and someone else comes along and says, well, I'm going to rotate my axes. So I'm going to rotate them by 45 degrees and say I'm going to call these new axes u and v. If you were using the first interpretation of matrix just as some bunch of numbers, you would say, well, the matrix is the same in either coordinate system. It's just a bunch of numbers. But from the modern perspective, we would say, well, no, a matrix is a particular linear transformation. So the matrix which transformed vectors in a particular way in the old system is mapped to a specific new matrix in the new system. So this doesn't make a lot of sense at the moment, but what I'm trying to get at is you should not think of a matrix as just a collection of numbers. You should think of the numbers as one particular avatar of some deeper object. Other thoughts or comments? Did I lose anyone?
I have none, and I think you like kind of paused there because Corbin made a noise. I don't know. I'm ready.
Okay, yeah, I mean, I wasn't sure if people were saying words, so okay, good. So that's the roadmap. Good. Then I don't think I need to save a screenshot of this one, so I will just clear. And now let me ask you too, since we're going to start discussing what a linear transformation is. So have either of you heard of the freshman's dream?
I believe I've seen a Wikipedia article on it once, but I have no idea what it is.
Okay, good. Then this will be fun. This is just to motivate why we should care about linear transformations. So this is called the freshman's dream. It's an incorrect equation. It's called freshman's dream because often people learning algebra for the first time will apply some wishful thinking and hope that this equation is true. That if you take kind of x plus y quantity raised to some power n, that would be the same as taking x to the n and adding y to the n. But of course this is not true in general. I mean, even just if n equals 2 for squaring two numbers, we know that x plus y quantity squared is not x squared plus y squared. There's an extra piece. What's the extra piece that's missing?
XY.
Or 2xy, right? Right, because when you FOIL them, you'll get 1xy from the outside and then 1yx, so it should be 2xy, right?
And now I remember why I saw a Wikipedia article on this, because back in Algebra 1, my father used to yell at me a lot for doing it.
Mm-hmm. Good. So this is, of course, not the same as x squared plus y squared. So it's a common mistake. I mean, people kind of look at this and they see parentheses, and you can often distribute across parentheses. If you have a number a times x plus y, of course you can distribute a across the parentheses. So people sometimes get a little trigger happy and think you can kind of distribute this process of raising to powers. And it's simply not true. Other things that are very similar, you might think that if you have a square root of a sum, that you can sort of distribute this square root and get a sum of root x plus root y. But that's completely untrue. Similarly, you might think that just as multiplying by a kind of distributes across parentheses, you might think, what if it distributes across a function like the log? So the log of ax might, you think, be equal to a times the log of x. But that's not true. I mean, as we know, it's by the the log of a product rule. This is something different, log a plus log x. Or more generally, something like the sign. We know that the rule for the sign of a sum is something more complicated. There's this angle addition formula. But if you were naively trying to distribute sign across these things, you might think, well, I can distribute it onto the first term and pull out an a and get a sine x and do the same thing to get a b sine y. But that's also untrue. So the moral of the story is that although all of these equations are false, you can kind of see why someone might apply this wishful thinking. Because if you can do this, if you have a function where you can sort of distribute the function across addition or multiplication by a, it makes life much easier, right? It would be a lot easier to simplify expressions involving that function if you could do that. It's just usually not true. Okay, thoughts, questions on this?
No.
None. Okay, is it obvious that all of these are untrue?
Yes.
Yes.
Okay, good. Good, making sure. All right, why do I bring this up? You might say, as we often do in math, that if a nice property which you would like to be true is not true in general, then you just ask the question, what happens if I make a new definition? I'll just define a certain class of functions to have the nice property I want, and then see what kind of functions have that property. So let's do that. Those equations on the previous slide are wrong because the functions are non-linear. They don't have this property of linearity. So here's our first definition. If you have a real valued function, f from r to r, so it takes in a real number and spits out a real number, we will say that function is linear if for any a, x, and y, all real numbers, you can take f of the sum x plus y and sort of distribute the f across the sum. So that's the same as f of x plus f of y. And if you have f applied to a product, a times x, you can pull out the a so that f of a times x is the same as a times f of x. You can kind of pull this out. So if those two things are always true, we'll say the function is linear. Okay, questions on this definition?
No.
So here's a question for you. How about the constant function? So if I say let f of x equal 1, so I give you any input, it always spits out 1. My question is that function f linear? So you have to check the definition. What do you think?
No.
No. So tell me why not. Give me the counterexample.
Since by the function that you gave, for example, if x equals 1 and y equals 1, f of 1 plus 1 is 1, which does not equal f of x equals 1 plus f of y equals 1.
Good. So you're saying add 1 and 1 inside the function, the output will be 1. Compare that to adding f of 1 plus f of 1, and that's going to give you 2. And of course, in most number systems, 2 is not equal to 1. Good. I agree. So this function, a constant function, is not linear. Good. Okay. So let me give you an example of a function which is linear, and I'll actually prove it for you. So we're going to consider a function that multiplies by a constant. Actually, I want to switch colors. My number of colors is more limited with this app. If you pay $20 for the full version, then they give you more colors, but I'm not going to do that. So, okay.
$20 for colors.
And I think a line tool, but I don't really need that either. So we consider a function which multiplies the input by a constant. So f of x equals 2 times x. Takes any input and doubles it. So I'm going to prove, or I have proven, that this function is linear, and to prove that we just have to check those two things in the definition. The first is that if you apply f to the sum x plus y, that should be the same as f of x. Oh, that's a typo. Plus, let me just scribble over that. That should be f of x plus f of y. Sorry. So let's think about the left side. So if you apply the function to x plus y, the function just multiplies by 2. So f of x plus y is 2 times the quantity x plus y. We can distribute the 2. That's 2 times x plus 2 times y. But that's the same as f of x plus f of y, because f of x is 2x and f of y is 2y. So the first property is good. Second property, multiplication by a constant. F of a times x, well, you simply double the input, so that's twice a times x. Multiplication commutes, so that's the same as a times 2x, but 2x is the same as f of x. So that's a times f of x, which means you can pull out a constant. So that means both properties are satisfied. And that means this function is linear, which is what we wanted to prove. And you can probably see right away there was nothing special about the number 2 here. If I'd replaced the number 2 by any constant c, all of the steps of that proof go through. You can simply distribute the c, and you can always swap the order of c and a. So I claim that any function which multiplies by a constant is linear. And as we'll see, I've claimed linear transformations are really the same as matrices. So if you'd like, you can think of this as our first simple example of a matrix. It's a 1-by-1 matrix. This is a matrix with one element, so I'll write it with square brackets. So it's a 1-by-1 matrix C multiplying a 1-by-1 matrix X, which is kind of silly, but it's the simplest example, and we'll build up. Okay, so does everyone understand why multiplication by a constant satisfies our definition?
Yes.
Yes.
Sweet. Other questions on this?
No.
Good. We are making good progress. Then I will turn it over to you. So we proved on the previous slide that multiplication by a constant is linear. Now we'll have a slightly different function. So now we let f of x be the usual form of a line you learn in Algebra 1, ax plus b, or maybe you write it as mx plus b. So think for a couple seconds and tell me whether you think, I don't need a full proof, but just whether you think this function f of x, which is the graph of a line, is this function f of x linear?
Are you just asking for a yes or no or a proof?
Well, the yes or no, but it doesn't have to be a proof, but I want some reasoning. There should be some non-zero thought included with why you think it's true or false.
I say yes because, well, my non-zero thought hopefully is that that is just the definition of a linear function.
Okay, so we
Yeah.
think yes. All right, so let's prove that lines...
But that's what that's just something I've been told, not a thought.
That's fair. So our reason, if we were asked to justify why we think yes, because the words sound the same, because these are linear functions, and this is a graph of a line, so the words sound similar. Okay, let's try to prove it then. So let's do f of x plus y, since we have to prove this is f of x plus f of y. So let me ask you, what should I put after the equal sign if I plug in x plus y into this function?
No, never mind. Oh, it would also be, it would effectively be a times x plus b plus a times x plus b. Wait, no, a times y plus b.
Let's see, so what is the rule for evaluating a function? So you take the input, and then everywhere you see that symbol on the right side, you substitute the input for that symbol. So I think everywhere we see x in this right side, we're going to substitute x plus y. So I think it should be
Oh my.
this.
Yeah, I have no idea why I thought that, because I was literally doing f of x plus f of y or whatever.
You were jumping ahead to the next step of the proof. But first, let's just do this. Let's do f of x plus f of y. Or sorry, let's do f of x plus y and then f of x plus f of y. So this part just comes from plugging in for x. So you substitute the sum x plus y everywhere you see x, which we've done. And then I'll just distribute to make this a little more explicit. Okay, now what's f of x plus f of y? So now there will be two terms. First, I just plug in x everywhere I see an x, which means this is unchanged. In the second, I substitute y everywhere I see an x. So what are the two pieces I get from adding these up?
So you would get a times x plus a times y plus 2b.
Good. ax plus ay plus 2b. Now, are these two lines the same?
No, but they are parallel.
They're parallel, but b and 2b, assuming b is not equal to 0, are not equal. So, in fact, the answer is no. So this is the first important takeaway of the subject, is that matrices fall into the field of study called linear algebra. I hate that name very much, because linear algebra makes you think of what you study in Algebra 1, like the algebra of lines, y equals mx plus b, or something. But the definition we've given on the previous slide of linear, which lets you distribute a function over addition, is not very obviously related to the graphs of lines in the plane. In particular, with our definition of linear, the graph of a line is not a linear function. So let me just write that explicitly. The graph of a line, y equals ax plus b or mx plus b, the graph of a line is not linear. Not linear. Unless, of course, b equals 0. So if your y-intercept vanishes, then it's linear. So I just want to emphasize that this is a different definition. We're using the word linear in a different way than the way you might be used to. Good. So is it clear now that that these lines are not linear, even though we maybe initially thought yes?
Yes.
Yes.
Sweet. Okay. Let's move on. Okay, so I'd like to actually show that we showed 2 slides ago that if a function multiplies the input by a constant, then it is linear. So now I'm going to show the converse, actually, which means that every linear function in one dimension, every linear function is multiplication by some constant. So in other words, the one-dimensional linear functions are very boring. There's only really one type of linear function, which multiplies by a constant. But instead of my reading the proof, I'm going to ask one of you to read the proof. So whoever would like to volunteer, could you read the proposition and then read the proof?
Orban is silent, so I'll do it.
Yes, I was going to say I volunteer Logan as tribute.
Proposition. Let the function... Okay, how do I don't quite know how to word this.
Let f from R to R.
Let f from R to R be linear. Then f of x equals c of x for some c in the real. Real?
Yep, reals.
In the reals. Proof. Let f be a linear function and let x be an element of the reals. Saying reals is weird. By the definition of linear, f of x equals x times f of 1. Define c equals f of 1. Then f of x equals c of x for all x. We conclude that the only linear functions in one dimension are those which multiply by a constant.
Good, okay. So let me ask either of you, whoever wants to answer. The key step here was this equality. So which property of linear functions did I use to claim f of x must be the same as x times f of 1? maybe I should rewrite them just see in case you forgot. So the two properties, if f is linear, is that you can distribute f over addition, and that if you multiply two numbers inside, you can pull one of them out.
I'm going to say you use the second one where you pull a out of the function.
Good. So,
Oh, wait,
what did you say?
that was a question. Whoops.
Yeah, sorry. Good. So I use the second one. What are a and x? Well, I've used the letter x twice, but what are the two numbers that are being multiplied inside, which I've used to apply the second rule?
1 and x.
Good. Yeah, so it's almost trivial. F of 1 times x, you can pull out the x, f of x times f of 1. And then we've just made a variable definition. I'm free to call c the number which is f of 1. So that's c, which is the f of 1, times, sorry, why did I say f of x? You can pull out x times f of 1. There we go. So the number a pulls out without an f in front of it. So this is c times x. There we go. Good. So this multiplicative property is too constraining, right? This is almost too strong of a property to impose, because if we impose this property, the only functions we get out are multiplication by a constant. And again, the way that we saw that is that if you plug in any arbitrary number, this rule tells you that the output for that input must simply be the input times the function evaluated at 1. So although our journey started by trying to classify all of the linear functions that have this nice property, the journey ended very abruptly because we realized that the class of all such functions is very boring. And this often happens in math. You say, I'm going to impose some condition which I like to try to find interesting functions, but the condition is too restrictive. So there's very few functions with that property. The way to fix this usually is to generalize. So you keep the same property, but you start with a larger class of functions, or a larger domain or range, to try to find more interesting ones. And this is the entire beginning of the subject of linear algebra. So we're going to try to generalize this. So we're no longer going to consider functions from R to R. We're going to consider a different domain and range to try to get more interesting linear functions. But before we do that, is this slide clear, and are there any other comments or questions?
No comments or questions.
No.
How do we feel about this so far? Boring, too easy, or just right, or too hard?
The former two.
Okay, boring and easy. Good. Okay. I'm told that when you give a talk, you should begin with everyone understanding and end with no one understanding. So I've done the first part right, at least. Good. Let me try blue. Okay, so we're going to go up in dimension, as I hinted at. So instead of functions from R to R, we're going to consider functions from R2 to R2. What do I mean by R2? R2 is the set of all ordered pairs x comma y. So for instance, you could have the point 2 comma 1, which is an element of R2. Now you'll see this, and oops, that's not a straight line. You'll see this, and you'll probably think, oh, this is boring. I've studied this already. I've learned in algebra that we can have an xy plane, and we can plot points like this, which have, say, 2 along the x direction and 1 along the y direction. So I already know how to study ordered pairs of two real numbers. But I'm willing to bet that in your algebra class, you never discussed what it means to add 2 points. So if these points are P and Q, I'm willing to bet that you never discussed what it means to add the point P to the point Q. Or maybe I'm wrong. Did you discuss addition of points in the plane?
No.
Okay.
No, but I think I know how it goes.
Yeah, I mean, you should do kind of the most natural thing you can think of, which is add the components. So if P is the point 2, comma 1, and Q is the point 1, comma 2, the most obvious thing to do is to simply add the first components, 2 plus 1, and also add the second components, 1 plus 2. So you get the point 3, comma 3. Now we'll see on the next slide a picture of this, but since adding these points doesn't really have a clean picture associated with it, I can't visualize what it means to add these 2 points. We will usually draw these points as directed line segments, or kind of arrows. So if you think of an arrow pointing from the origin to P, and then a different arrow, maybe in pink, going from the origin to Q, then the interpretation of adding those arrows is just to take one of the arrows and then append it to the end of the other arrow. So if I add P to Q, that's supposed to be the same as taking the tail of this arrow P and adding it to the head of the arrow Q, right? So you just put the 2 arrows head to tail and add them to get a new point, which is supposed to be 3, 3, although I haven't drawn it very well. So the arrows are just a visual mnemonic for adding these points. Okay, good. So that's the geometry. What's the algebra of this? So again, we're discussing all ordered pairs of reals. We define addition in the most obvious way you could think of. You take 2 ordered pairs x, y, and say uv, and add the first components x plus u, add the second components y plus v. We also will need to multiply an ordered pair by some constant. So to distinguish between ordered pairs and constants, a constant is not a pair, it's just one number. We're going to use these words vector for an ordered pair. So a vector is some ordered pair like x comma y. And we'll use the word scalar for a number, which is like just c. And again, the most obvious thing you could think of is to multiply a scalar by a vector by simply multiplying each component. So for instance, if I multiply 5 times the vector 1, comma 2, we'll define that to be 5, comma 10. And you can, if this is an arrow, you can think of this as just stretching the arrow by a factor of 5. So you kind of put 5 of those arrows head to tail to extend them. Okay, so this is what we mean by vector. If we had more time, I would give you the formal definition of a vector space, which a vector space is any mathematical structure where you have some symbols which you can add and scalar multiply in this way, which don't have to be ordered pairs of numbers. They could be anything. They could be polynomials or more complicated objects, as long as you know how to add and scalar multiply them. But for our purposes, we will just consider kind of ordered tuples of numbers. So we're going to take a somewhat more concrete case. So the takeaways here are vectors are ordered pairs. We can add them. We can scalar multiply them. And the final takeaway is that although it's often easier to write them with parentheses, especially if you're trying to save space, later I'm going to exclusively write them with vertical columns like this. So you put the first component on top and the second on bottom. So A1 and A2 will be the top and bottom components. Okay, good. Lots of stuff, but thoughts on this?
It seems really intuitive, so I'm scared to see the part where everything goes to hell.
I think it should stay intuitive. I mean, matrices are, I think, a lot more concrete and down to earth than calculus. So the intuition, I think, hopefully will not go away. So by that comment, I assume that this is still pretty obvious and tractable. Is that you're following this like 90+%, you'd say?
Yes.
Yeah.
Good. Okay.
Oh god, my voice is terrible compared to all of your guys.
Lol.
Mike's for the win.
Okay, so let's draw some pictures. This is just a better version of the drawing I had on the previous slide. So if you have a vector A, which often to emphasize that something is a vector, people will use bold. So here's a bold A. So A is the vector, which means the ordered pair. So the first component is the kind of distance along x you would have to go. The second component is the distance along y. And again, we visualize that, even though it's really just a point, we visualize that as a vector pointing from the origin to the point, or a directed line segment, I guess, an arrow from the origin to the point. So a vector we draw as an arrow from the origin to the point, kind of a1 comma a2, or x comma y. Okay, let's see how to add those. So again, a better version of what I was trying to draw before, but if you have a vector A, which has an x component a1 and a y component a2, so here's a1, for instance, on the x, and a2 on the y, and a second vector b, so b1 in the x direction, b2 in the y direction. This vector addition I was talking about comes from simply taking the vector b and moving its tail to the head of vector a. So if you first go along the arrow a, and then go along the arrow b, this gives you the vector a plus b, which in components you could see is just the same as adding the two components of a and b. So a1 plus b1 and a2 plus b2. So it's geometrically adding head to tail, algebraically just adding the components.
Okay, yeah, this picture. Earlier, I was going to say that it looks like this middle line, that is the addition of the two, looks like the just halfway between the two angles. Yeah, that's a great explanation. But yeah, that makes sense now.
Interesting. You're thinking about these two angles, you're saying?
Specifically, the two interior ones and how they're identical. I forget the name for that.
Ah, yeah. So you're saying that these two interior angles are similar or identical. They're equal.
Yeah.
Okay. Yeah. The reason for that is that the sum of two vectors is always going to determine a parallelogram in the plane. So this is simply the geometry statement that the diagonal of a parallelogram always bisects the angles, right? I don't know if you learned that, but this is just a geometry.
Well, I kind of had to memorize it. You know how geometry is.
Mm-hmm. And in fact, I think, yeah, it's problem 1. When you see the matrix challenges, which I posted and is due Sunday midnight, Sunday 11:59. So the first question on the matrix challenges will ask you to find the area of a parallelogram determined by two vectors. So you'll kind of do a picture similar to this, and then hopefully you remember that how to find the area of a parallelogram. You just need to find the height associated with the given base. And yeah, it's very geometrical. So good. Other observations or comments on this slide?
I do not.
Nope.
Sweet. Okay, let's keep on trucking then. So the other thing, we can add vectors. We can also multiply them by scalars, which are just numbers. So if here's the vector a, which goes from the origin to some point, you can kind of imagine that if you just double the two coordinates of that point, this is what I need. If a were, for instance, 2, 1, then doubling each of those coordinates to, say, 4, 2 is simply going to stretch the vector by a factor of 2. So multiplying by a positive number stretches the vector, multiplying by a negative number, like -1. So for instance, this would be -2, -1. That simply reverses the direction. So geometrically, multiplication either stretches or reflects across this vertical axis. Good. Okay, now a challenge for you. So, I have to draw it because it's on my screen, but I will ask you to tell me what to draw for each of these. So I've given you two vectors, u, which is 2, 1, and v, which is 0, 3, using this column vector notation I'll switch to. And the challenge asks us to draw u, v, u plus v, and u minus v. And then we'll do something else, but first I want to draw these. So first, to draw u, what should I describe to me what I should draw?
I believe you should start drawing u by drawing a line from 0, 0 to the coordinate point 2, 1.
So from 0, ooh, that's not very good.
Whoa!
0, 0 to 2, 1. So this will be the vector u. Good. Okay, what is the vector v then?
Vector v would be, in this case, drawing a line from 0, 0 to 0, 3, which is vertical.
Good. So vertically upwards to 0, 3 will be v. So now, as an intermediate step, when I add u plus v, what are the components of u plus v?
In the first place, there would be 2, and in the bottom, well, quote unquote bottom, there it would be 4.
Good. And how do I draw this?
A line going from 0, 0 to 2, 4.
Good. So I can't actually quite fit that, but you'll have to imagine. Here's u plus v going up to 4. 2, 4. Okay, how about u minus v?
U minus v would be the vector 2, negative 2.
2 minus
Negative
2.
2.
Good. Okay, and then I will not torture you any further. 2 minus 2, of course, goes from the origin to the point 2, negative 2, which is down here. Okay, last and the more interesting question, adding two vectors and then trying to find coefficients a and b so that the sum of the two vectors is a particular given vector. So this is kind of like reverse engineering, if you say. So we have a vector which, for instance, is minus 2, 0, and I ask you to find two numbers a and b so that if I take a times the vector u plus b times the vector v, the sum of those vectors will give me this thing, minus 2, 0. So first, I should write down an equation first to make this a little easier to parse. What should I write down? What equation should I write down in order to understand this?
I do not know.
Well,
Does Corbin know?
Nope.
well, it's okay not to know, but it is not okay not to think. So what do you think would be, if a is some number, let's start with an easier question. So if a is some number, what is the vector a times u?
A2 and A1.
Yeah, or I'll say it in the other order, so 2a and a, right? A times 1 is always a. Okay, what is the vector b times v if b is some number?
0 and 3b.
0, 3b. And then we want this to be equal to minus 2, 0.
Oh, that's nice.
Good, so if I
I
combine
was
the left
not
side.
aware we could do that.
Yeah, this is, remember I said you can scalar multiply vectors and you can add them. So first we scalar multiplied. What happens when I add them now? What happens on the left side?
Well, it would add up to 2a over, let me
3ab.
think.
2a over 3ab. Or 3b plus a.
Yeah, 3b plus a.
Multiplication and addition are not the same things.
In most cases, no. All right, so one of these
Most.
is easy. What
Most.
should a be?
I believe we can set a to negative 1 and then change b until it works.
Yeah, so a is minus 1. Because remember, these vectors have to be equal, so both components have to be equal. So we set the top components equal. 2a is minus 2, which gives a is minus 1. Then we set the bottom components equal, but I'll go ahead and substitute minus 1 for a, which means 3b minus 1 equals 0. And, I mean, you've probably been assigned worksheets where you have to do 100 of these, so now what is b?
1/3.
1/3. Good. Alright, so good. The punchline is that now you see how to add and multiply vectors, and you also see that we can form equations which involve adding and multiplying vectors to get a new vector and solve those in the same way we solved equations to get numbers, in the same way you would have I don't know, ax plus by, or I don't know, whatever. Good. Other thoughts or questions or observations on this slide?
Is this video being posted?
Yeah, I don't see why not. Why?
Just curious.
Why, I can make it unlisted if you're embarrassed for some reason.
I was just curious if you're going to be titling it Introduction to Matrices or something.
Yeah, I'll probably call it Matrices 1 or something like that.
See, I get an odd anxiety from the fact that this will be posted and that I'm answering questions. Because if I make a mistake, then it is out there.
That's fixed mindset thinking. Mistakes are the best kind of thoughts to have because you learn from them.
Yes, but I don't like making mistakes in front of people. It's strange.
Yeah, well, get over it.
Wait, you're embarrassed for being human. You don't belong here.
Sorry. I also still have not finished Carol Dweck's book. Dweck's? Is that how you pronounce it?
Dweck, D-W-E-C-K.
Ah.
Alright, so now we know what vectors are. Let's go back to the main thread of the story. So you'll recall our quest here is to classify linear functions. We've already classified linear functions in one dimension, which means R to R. And we found the classification was very boring. There's only one kind, multiplication by a constant. So now we're going to go up in dimension since we know what two-dimensional vectors are, vectors in the plane. We're going to ask what are linear transformations of those vectors. So here we go. Let f be a function from R to R. That means f takes in a vector, so maybe it takes in a vector u, and spits out some other vector v. Right? So it just takes a vector and gives you a vector. Now we're going to make a very similar definition. We say that f is a linear function, or a linear transformation, if f applied to the sum of two vectors, u plus v, is the same as f of u plus f of v. So this looks very similar to the definition we had before, but now you have to remember u and v are vectors. So this is really, u1, u2 plus v1, v2, right? This is saying you apply this function to the sum of two vectors. And that's the same as applying the function to either vector and then adding them. Similarly, now f applied to a number a times a vector. So again, this is scalar multiplication, which means a times the vector u1, u2, which, as we've seen, just means multiply each component. That must be the same as a times f applied to the vector u. So same definition as before, but now every input is a vector, u and v. And this must be true for all vectors u and v and a number a. So a is a scalar, by the way. A is not a vector. I've combined those two conditions into one condition where you apply f to a times a vector u plus b times a vector v, and I've just put both rules together into one giant rule. So if you do that, f of au plus bv is a times f of u plus b times f of v. So again, this is au plus bv, and here the input is u, and here the input is v. So a different way of writing the same thing, but just making the column vectors explicit. Okay, so is it clear that this is the kind of the natural generalization of the definition of linear we had before?
Yes.
Yes, I've also noticed that this is basically the truthful part of the freshman's dream.
Yeah. You could describe all of linear algebra as being very butthurt that the freshman's dream is not true, and then deciding, well, I'm only going to consider functions where it is true, right? You're going to say, all right, now let's just consider linear functions where the freshman's dream actually holds, right?
So it's a revenge mathematics.
Yeah, you could say that.
That's good. Okay. I've also noticed that the second vector you're adding, if you look at it from far away enough, looks like a graffiti M.
The second vector, like in components, you mean? Down here?
Although the first one that you drew.
First one that I drew. Oh, up here. This thing.
No.
Or here.
The one on the right there. It looks like an M. Why does this amuse me so much?
I have no idea. You mean the V and 1 connect to look like an M or something?
Yeah.
Oh, I see it now.
I don't know, maybe it's just
I've been around Jake too much. I'm sorry.
poor
This
him.
is painfully obvious. I live with him.
All right, now some concept questions for you. Okay, so now we understand linear functions in 2 dimensions. So now I will ask you to use the assumption that a function is linear and that I've given you some of its outputs to figure out other outputs. So maybe just to go back one slide to remind you of what you're allowed to use. So I'm telling you f is linear, so you're allowed to use that f applied to a sum is the sum of f applied to the individual terms, and you're allowed to use that f applied to the multiple of some vector is the multiple of f applied to that vector. These are the 2 rules you can use to figure out other outputs. So now let's use that. It's kind of like a puzzle to figure out other outputs given some outputs. So we assume f is linear, so we can use those 2 rules. And I'll tell you 2 pieces of data. If I apply f to 1, 0, then I get this vector a, b. It doesn't matter what a and b are. You assume that these are 2 known quantities, a and b, so these can appear in your answer. So you know this. I also tell you f applied to 0, 1 is this other vector cd. Again, these are known, so they can appear in your answer. And now you have to use these 2 pieces of data and the linearity rules to figure out what is the output of f applied to other inputs. Cool? So first one, if I apply f to the input 2, 0, can we figure out what that must be using the given data?
I believe that we can, not much reason behind this, but I believe that we can say that this is 2a over b, quote unquote,
So,
because I said over like it's a fraction.
so you say 2a and b are the components. Okay, so what is the rule? So I think you're trying to say this is, we can write this vector 2, 0 as twice the vector 1, 0, right? That was your idea under the hood?
That makes 0 sense now that I think of it.
Okay, well, I mean, let's just follow this line of reasoning. So the input is 2, 0, and if we pull out a factor of 2, then we're applying f to the number 2 times the vector 1, 0. Now, we can apply one of those 2 rules I showed you on the previous slide to simplify this. What should I simplify it to?
I keep turning off my mic. So
Yes, I was curious why you were muting yourself.
anyways, this can simplify to, well, quote unquote, simplify to 2f of the vector 1, 1, 0.
Good. And then what is the vector f of 1, 0?
And that is ab, so 2ab.
Good. And how do we multiply a vector times a scalar?
In effect, distribute it.
Right. So what are the 2 components of the top and bottom, as you call them?
2a and 2b.
2a and 2b. Okay, so our initial guess was almost right. You said 2a over b. We shouldn't use the word over. We should say the vector 2a, b. And really what it should be is 2a, 2b, right? Because the 2 multiplies both components. So I think this is the correct answer. F of 2, f of 2, 0 is 2a, 2b. Do we agree?
Violent noises.
I just heard a loud crash. I don't know if that's agreement or disagreement.
It's both.
It is very violent agreement.
Okay. Good. Let's use a similar strategy. So to find f of 0, 0, I claim you can write 0, 0 in a very silly way as a particular number times one of these inputs. So how should I simplify f of 0, 0?
I was going to ask if we could write it as f of 0 times vector 0 over 0.
F of 0 times, well, we want this to be f of 0 times a vector whose output we know, right? So why don't we pick a different vector? Sorry, what were you saying?
Could we do the one that we have above, c over d?
Let's see, the output is c over d, so you want to pick the input to be 0, 1? Is that the suggestion?
Yes.
Okay.
Oh boy.
So I agree that 0, 0, the vector 0, 0, which is just the origin, is the same as the number 0 times the vector 0, 1, since you distribute the zeros and then you get 0, 0 in a very silly way. Now, what rule do I apply to simplify this expression?
The same one we applied above, where we take the constant and move it outside of the function.
Good. So
Is that really going to get us anywhere, though?
Yeah, I think it does.
Oh, wait. Okay.
Now, what is f of 0, 1?
F of 0, 1 is C, D.
Good. And now we can, again, scalar multiply. So what is 0 times the vector cd?
0, c over 0, d.
Yeah, which I'm just going to not
Zero.
write the c and d. Good. Very good. Okay, so you may have noticed that the values a, b, and c and d played absolutely zero role in the second question. Regardless of what they were, we could have played the same game and said pull out a 0, and then it will be 0 times whatever this function is, but 0 times any vector is 0. So this is a general rule. For any linear function, this only applies to linear functions, for any linear function f, we have to have the result that f applied to the 0 vector, 0, 0, is also the 0 vector. You can never send the 0 vector to something non-zero and still be linear.
This makes sense because in the first dimension, adding a constant made it no longer linear.
Yes, exactly. So that's why in f of x equals this 1 by 1 matrix C times x, that was linear if we did not add b. But if we attempted to add a constant b, that would break the rule that you must map the 0 vector to the 0 vector. If we tried to do this, we would map the 0 vector to b, which does not work. Very good. Okay.
I like how it appears that you made the slide today.
Oh, because it says July 13th?
Yeah.
There's actually a line of LaTeX code which is just /today, which will automatically change the date so that it always looks like you made it today.
What a great command.
I love it. Okay, is this slide happy? Good.
Yes, it makes sense. Is there some specific LaTeX command for making matrices, or do we just use square brackets with /left, /right?
No, there is a good command. It's /b matrix, and I will post something probably on Piazza that tells you, because there's /b matrix, then you have to put extra stuff afterwards. So I'll tell you what the extra stuff is on Piazza, probably.
That'll get fun.
Yeah, the alternative is just do these on pen and paper if you want. Okay, 2 more questions on this same topic. So, well, I've deleted everything, but hopefully you remember what they were. So now I'll ask you 2 slightly harder functions applied to these, like 2, 1 in terms of the input. So now instead of just multiplying, the other ones were 2, 0 and 0, 0, so it was simply multiplying one of the 2 that we know by a constant. Now you will need to both multiply and add, and use both rules. So I'll ask you, what should I do to evaluate f of 2, 1 in terms of our 2 given data points?
Could we simply subtract 1, 1
Subtract.
to get slightly closer?
So you want to subtract 1, 1 from the input. Okay, so you're saying this thing should be...
Yeah, that doesn't quite make it equal.
Yeah, I think it would work. It would give us an equation we'd have to solve. I think there's a simpler way to just express this input as a number times one of these vectors plus a number times the other vector, which would make life a little easier. So how can I write 2, 1 as a sum of two vectors that are multiples of the vectors, the input vectors whose outputs we know?
So we could say that it is 2 times 1, 0
Good.
plus 1 times 0, 1.
Good, that works. Now f is linear, so you can split this, right, as 2 times f of 1, 0 plus 1 times f of 0, 1. And now we know what these two things are, so what is the result after I plug in these two expressions and combine them?
Deep thinking. So on the top, it would be 2a plus c, I believe.
Good.
Yeah, that looks right. And on the bottom, quote unquote, it would be 2. Let me think. Yeah, 2b plus d.
2b plus d. Good.
Doesn't feel. Yeah, that's good. Yeah.
Because the first one is twice ab, so there's a 2a and a 2b. The second one is cd, so we have a plus c and a plus d. Good.
Okay.
Very good. I'll do the last one for you, because now you can kind of generalize this pattern. We saw that if I give you two data points, I give you f of 1, 0 and f of 0, 1, we can figure out a lot of other shit, right? We can figure out the function's output for inputs that don't look like those two. So let me show you a trick. I'm going to apply f to a completely general input, u1, u2. These can be any numbers at all. u1 and u2 are completely arbitrary. So in particular, every possible input has this form for some choice of u1 and u2. Now watch this. So f of u1, u2, we do the same thing you just told me for question 3. You simply take the first component and multiply that by 1, 0. Here the first component is u1. So f of u1 times 1, 0. So that gives us u1 in the first slot, which is what we have in the input here, plus u2 times 0, 1, since that gives us, multiplying u2 across each component, u2 in the bottom slot, which is what we have. That's the same as u2 times f of 1, 0, using linearity, using one of the two rules, actually using both of the two rules, plus u2 times f of 0, 1. And now we know what these two things are. We know f of 1, 0 is ab, and when we multiply that by u1, we have au1 and bu1. And similarly, when we multiply u2 times f of 0, 1, we have cu2 and du2. So I'm going to do this all in one step. We're going to have au1 from the first term, and then we're going to have cu2 from the second term. And on the bottom again, we have bu1 from the first term and du2 from the second term. So it was a little fast, but we took an arbitrary input u1, u2, split it as u1 times 1, 0 plus u2 times 0, 1, used linearity to break that into u1 f of 1, 0 plus u2 f of 0, 1, and then plugged in those two known vectors, f of 1, 0 and f of 0, 1, and then combined to get the answer. Okay, so that was a lot of steps. Questions on that procedure?
I don't have any questions.
Okay, so you agree with the result?
Yes.
Yes.
Good, okay. So, I mean, the procedure is all well and good, but let's think about the punchline of what I just showed you. This means that if I give you a linear function and I tell you its outputs for just two inputs. I tell you its outputs for 1, 0 and 0, 1, which is kind of completely determined by these four numbers, a, b, c, d. So I just hand you four numbers that describe the outputs of that function for 1, 0 and 0, 1. Then any output of that function, f of u1, u2, for absolutely any u1 and u2, is completely determined. We know the answer in terms of those a, b, c, and d, right? If I hand you any u1 and u2, and you know a, b, c, and d, you know what the output of this function must be. You just write down au1 plus cu2 and bu1 plus du2. So at the beginning, this seemed like this function could be very complicated, like a nonlinear function like f of x equals sine x. It would be completely hopeless for you to expect to know all of the outputs of this function if I just give you four numbers, right? I give you a, b, c, and d, 4 data points along the curve. You would not be able to figure out all of the other outputs from 4 data points. So there, it's a hopeless question. But here, if f is linear, I just give you those 4 numbers which describe outputs for 2 inputs, and now we can figure out any other output. Any other f of u1, u2 is completely determined. So these linear functions, the upshot of all this is these linear functions are very, very tightly constrained. You only need 4 numbers to tell you absolutely everything about the function. Does that make sense, and or are there questions?
Yes and no.
Good. Okay, so let's see, we're about an hour in and about halfway through, which is good.
Oh, geez. Only halfway through. That's fun.
Well, sorry, I mean, there's a lot of content. We have to get through basically a course on matrices in 4 sessions, so.
Yeah, 4 sessions to quantum mechanics.
Yeah, it's going to be a little rushed and a lot of stuff.
I am enjoying that the time is passing by very quickly, though. It does not feel like an hour has gone by.
Good, that is comforting. That makes me feel better about myself. Okay, so this slide summarizes what I just said. So the whole point of that exercise was a linear map. That's a really non-straight line. It's a very gay line. A linear map on R2 is determined by 4 numbers. That's what I said. If f is linear, so that you can multiply, you can pull out the ax, and you can add, those 2 things that we wrote down. If f is linear and you know its outputs for these 2 inputs, 1, 0 and 0, 1, then you know its output for any input whatsoever. Any input. So we know the function's output for any input in terms of those 4 numbers, a, b, c, and d. So this suggests a change of notation, because up until now we've been writing linear maps f as a single letter f, right? So we write f with parentheses applied to this vector u1 and u2. But now this suggests maybe we should pick a different way of writing the function f, which makes it totally clear that the function f only depends on those 4 numbers, a, b, c, and d. And that's what we'll do in this next slide. So we're going to rewrite, instead of using the letter f, we're going to say this function is determined by an array called a matrix. So the first half of the slide is the same. Now we're just going to change the way we write f applied to a vector. So now a function f, for which we know its outputs at 1, 0 and 0, 1, they're a, b, and c, d, we're going to write that function f applied to u1, u2 in this way. And let me just emphasize, this is a definition. We're simply defining what we mean by this symbol. When we write the symbol, which is a square matrix of numbers times a vector, we simply mean the output of the function f, whose, with the properties determined up here, then f of 1, 0 is ab and f of 0, 1 is cd. The output of that function f is what we mean by this combination of symbols, a matrix times this vector. So there's no magic here. We can't prove this or derive this. It's just a definitional choice. So, sorry, go on.
It didn't dawn on me until now that this is why you were making the matrix references.
Oh, because everything before now seemed to have nothing to do with matrices.
Matrix.
Oh, the
The
movie.
Matrix.
Oh, yes. In
Yeah.
Slack, yes. The Neo references. Right. That's why I was doing that. Good. Okay. One other comment. So, even though this is a definition, I'd right away like to introduce one mnemonic, just a memory aid to remembering what the output of this function is. Since right now we're just writing, this is kind of a definition of this collection of symbols, but it's already useful to think of a particular way of remembering this expression up here. AU1 plus BU2 on the top, and CU1 plus DU2 on the bottom. So to remember that, it's helpful to think of a procedure where you match up a horizontal line of elements on the matrix with a vertical line of elements in the vector. What do I mean by that? I mean the mnemonic is that to get the first component of the output of the function, you take A times U1, so this is the horizontal line times the vertical line. So A times U1, and then you take B times U2 plus B U2. That's the first component. And now in a different color, to get the second component, you take this horizontal line and this vertical line. So the first element on this horizontal line is C. The first element on this vertical line is U1. So CU1. Now the second element, D, paired with the second element, U1, U2, plus DU2. So what you do again is take a horizontal line and a vertical line, and then multiply the numbers which come paired, and then add the two pairs. AU1 plus BU2, CU1 plus DU2, that gives you the output of the function. So let's just practice that very quickly. I'll pick specific numbers for these A, B, C, and D. So if I have 1, 2, 0, minus 1 times the vector 1, 1. So I'll ask you to tell me what are the two components, the top and bottom, which come from this horizontal line, vertical line pairing. So what's the first one when I take this horizontal line and this vertical line?
On the top you have 1, 2, and on the bottom you have 0, -1.
With a plus sign between them, right? So you said 1, 2, but you mean 1 plus 2, right?
Yeah. Whoops.
Good. So 1 plus 2 and 0 plus a -1, which is, in, again, most number systems, 3 minus 1. Good. Let's do one more. So 1, 1, 1, 0 times 1, 0. So again, top and bottom, when I do this procedure, what do I get?
Is Corbin there?
Maybe not, did he? Oh, I have a message on Discord.
He's there.
Oh, I will be back in a moment, he says, but that was 14 minutes ago.
Oh, okay. Yeah, didn't you notice he vanished? Whoops.
Whoops.
So on the top you have 1 plus 1, on the bottom you have 0 plus 0.
So why 1 plus 1 on the top?
Because you have... I'm just seeing it as distributing the 1.
So on the top we have 1, 1, and then 1, 0, right? So you take the horizontal line and the vertical line. So 1 times 1 plus 1 times 0, right?
Wait. I'm now...
Do you see it? So the top you take this horizontal...
Oh my god, I totally missed that. I was not understanding at all why you're going over the, what's proper? Your mnemonic.
Yeah.
Totally, I thought that it was on the top it was AU1 plus BU1. Just,
Yeah.
I was so absorbed in my own thoughts.
No. So you
Okay, that
I
makes
have
sense.
returned.
good. So
So,
the mnemonic is to take the horizontal line and the vertical line. You multiply first one, second one, second one. So in this example, first one is 1, 1. So there's a 1 times 1. Second one is 1 times 0, right? So
okay.
right. So what's the second component?
So on the bottom, you would have 0 plus 0.
0.
0 times 1 plus 1 times 0.
Good. So it's 1, 0. Okay, good. So this is just a mnemonic so far because we've only made a definition. So there's no magic here so far, but you still need to know this rule because we're going to multiply vectors by matrices all the damn time.
Oh Jesus, what have I missed?
We learned how to multiply a matrix times a vector. So I will repeat another example for Corbin's benefit. So
Sorry.
if we have, say, 1, 1, actually let's not do that, 1, 1, 1, 0 times 1, 0, we defined this notation where you multiply a square array of 4 numbers, a, b, c, d, times this column vector u1, u2. We defined this via a certain mnemonic, and the mnemonic is to get the top component, you take this component times this component, so 1 times 1 plus this component times this component, 1 times 0. So 1 times 1 plus 1 times 0. And some people like to think of this as taking a line. You take a horizontal line here and a horizontal line here and kind of match the numbers based on where they occur along the line. So 1 occurs first, and that's multiplied by 1. And then this 1 occurs second, which is paired with the 0. So 1 times 1 plus 1 times 0. And I just want to undo this because now it's become a huge mess. But the upshot of that is that the first component is 1 times 1 plus 1 times 0, which is 1. The second component, you do the same thing. So you take 1 times 1, and then 0 times 0. So the second component is 1 times 1 plus 0 times 0, which is 1. So again, horizontal line, vertical line, pair, multiply, and add.
This seems a very strange way to do things, but okay.
Yeah, I mean, it's not the most natural notion of multiplication between this square array and this column vector, but the reason we introduced this is because we saw on the previous slide that this function applied to any u1, u2 is totally determined by these 4 numbers a, b, c, and d. So if we're going to rewrite the function f in some way that depends on a, b, c, and d, we want to arrange those a, b, c, and d in a way which reminds us of this output, right? So look at this output. The input is u1, u2. The order that a, b, c, and d occur is a, b, c, d. Right? That's what we proved one slide ago. So if you're just going to pick a notation that reminds you of that order, where kind of A is in the northwest and B is in the northeast and C is in the southwest and D is in the northeast, the maybe natural way to remind you of that is to take those 4 numbers A, B, C, D and put them in this square and then put U1 and U2 to the right of them. So we kind of gain the benefit of this is that it reminds us of the order of those numbers in the output, but the loss, the drawback of this notation is that the mnemonic to remember how to convert between the two is a bit complicated. But okay, so at least is it clear that this arrangement of the numbers is supposed to be reminiscent of that of the output?
Yes.
Okay. Other questions on this?
No.
Good. Okay. Onward. Okay, so now you're just going to hammer several examples on this until it becomes automatic. So I've given you a matrix M, 1, 1, 1, 0, which I think is the same as the one that I showed a moment ago when I was drawing, 1, 1, 1, 0, and an input vector u, which is 1, 0. And remember, a matrix is just a function, so I've used this notation, function M applied to input u. So it's a function applied to an input, but we defined a particular notation which writes a square array like this times the column vector here. So I'm just going to write this to help you. But suppose we do that. Now I'll ask you, what are the two components of the output?
One and 0.
Let's see, the first one is 1 because it's 1 times 1 plus 1 times 0.
Or sorry, 1 and 1.
Yeah, 1 times 1 plus 0 times 0, so 1, 1. Good. Okay, so that's the first one. Now we're going to compose that function. So m applied to m of u. So we computed m of u up here. That's this thing, 1, 1. Now we are asked to apply the function m to the output m of u, which is this thing. So that means take m, which is 1, 1, 1, 0, and apply that to m of u, which was computed above, which is 1, 1. And now you will do the same procedure and tell me what this is.
2, 1.
2, 1. Good. Okay, so now we're going to iterate this. So keep in your head it was 2, 1 was the last one. So now we're going to do 3 times. So m applied to that output, so 2, 1 was the last output. Now we're going to apply m again. 1, 1, 1, 0 to this. Now what is this output?
3, 2.
3, 2, and now one more time. You will probably see a pattern pretty soon. What is the matrix M applied to 3, 2?
5, 3.
5, 3. All right, so let me ask you to think for a moment. Corbin might be more likely to recognize the pattern since you have worked with this recently. Do these numbers, so again, we started with, let me rewrite them. So we started with 1.
I wonder if they're the Fibonacci number.
Yeah, I was about to say, this is Fibonacci.
Yep. Okay, so yeah, we're 5, 3. This matrix 1, 1, 1, 0 repeatedly applied to an input vector 1, 0 defines the Fibonacci numbers. You can see that applying this one more time to 5, 3 is going to give us 8, 5, and so forth. So this is a preview of a result we will see in Matrices session 3, that you can write down an exact formula, not an iterative procedure. You can write down a formula where you plug in a number n, and it will give you the nth Fibonacci number exactly using matrix technology. So this is our hint of that. But I'll stop talking about Fibonacci numbers now that you've been seeing that hint. So other questions or thoughts on this slide?
No.
Not on this slide, but is my mic actually super obnoxious right now, or is it just playing through Corbin's thing?
Doesn't sound obnoxious to me.
Okay.
I have
just
push
checking.
to talk on.
Okay. I was concerned. So yes, I see what's going on.
Good.
Cool.
Okay. Next thing. So now, in the last slide we saw that you could repeatedly apply a matrix M to a vector U over and over. So M times U, M times M times U, and 3 times and 4 times and so forth. So you could ask the question, rather than applying M 4 times, so you multiply M times U and then multiply M times that result over and over and over, you could ask, could I find one matrix, a single matrix, which I'll write as M to the power 4. Can I find one new matrix, M to the power 4, so that multiplying that matrix, M to the power 4 times U, will give me the same result as applying m to u 4 times. So remember, m applied to u 4 times was this thing 5 times 3. So you could ask if I'm too lazy to iteratively multiply a matrix times this vector, could I just find a single matrix that will do it in one step? Right? Laziness. You just collapse it to one step. So I claim the answer is yes. Here's kind of the steps. So we're trying to find a matrix m to the power 4 times u, which will give us that output 5, 3, which we saw in the previous slide. So we would like to find 4 numbers a, b, c, and d, with the property that if we matrix multiply that times the vector 1, 0, we will get 5, 3. So I think that this matrix will work. If we put 5 and 3 in these two positions, then when we matrix multiply, we will get 5 in the first slot and 3 in the second slot, which is the same as what we found on the previous slide. Now you could reasonably ask why did I put 3 and 2 in the second column, because it seems like they didn't enter at all because they multiplied 0. And the answer is, well, to figure out what these are, you would also need to apply m to a different vector like 0, 1 to figure out how it should depend on that bottom position. But I've skipped that step for the sake of brevity. You should trust me, I guess, or work it out if you'd like on your own, that if you pick a different vector to find what the other two components have to be, you will find 3 and 2. That's kind of an aside. The upshot of the whole discussion is that this is a general phenomenon. Any repeated application of matrices, even if it's not the same, this was the same matrix applied twice to one vector u, and we can find a new matrix m squared which has the same output if you apply to a vector u. This is true even if you have different matrices, m and n, which are different linear functions from R2 to R2. If you apply m and then apply n, you can always find a single matrix, which I'll call mn, so that applying that single matrix will give you the same output in one step as you would get from composing m of n of u. You can always find a single matrix that will have the same effect in one single step. And in the next slide, I will show you how to find the elements of that single one-step matrix if you know the elements of the two matrices you're composing. Okay, thoughts on this slide?
Not really.
Is the idea still clear, or are we getting slightly more lost?
It's still clear.
Good, okay. Okay, so this is the hardest slide then. This is, I've been avoiding proving things. This is the only thing which I really want to prove. Oops. So I'll show you the proposition and then the proof. But I'll ask you to read I'll ask one of you to read the proposition first so that I can have a drink of water. So whoever would like to do that, please do so.
Do you want me to read it, Logan?
Sure, you can do a thing.
Of course. Proposition. Let m equal, I say that a, b, c, d, right?
Sure.
Let m equal a, b, c, d, and n equal p, r, q, s. Then the repeated application m of n of u on a vector u equal to u1 and u2 is the same as applying single matrix mn equals ap plus br, cp plus dr, aq plus bs, cq plus ds.
Good.
Wait, that's the order you're supposed to read it?
Well, he read it in the order this one, then this one, and then this one and this one. But I normally go top left, top right, then bottom left, bottom right. But otherwise, the reading was fine.
Okay.
Good. Okay, so what is the proof of this? Now, this is kind of a pain. This is the only hard proof. If we get through this, then it's back to fun. So all I need to do is prove that if I compose the functions m and n applied to an arbitrary input u, u1, u2, then the output of that composition will be the same as the single function, which I've written here, m times n, applied to the vector u. If I've proven they're the same for any u, then I'm done. So I'm going to do that. First, I'm going to calculate this expression, m applied to n of u, and to do that I first calculate the inside part, n of u. So that's the first step. First, apply n to u, that's the inside. Applying n to u, I'm just going to write it out. N times u, well, n is PQRS, so I write PQRS. U is U1, U2, so I've written that here. And then we just apply our usual, horizontal line, vertical line bullshit. So P times U1 plus Q times R2, P times U1 plus Q times U2 in the first line, and then R times U1 plus S times U2 in the second line. So again, R times U1, S times U2, and you add them. So this is the usual rule. This is the definition we wrote down a couple slides ago. That's n times u. Now the hard part is applying m, because remember we're trying to compute m of n of u. We have n of u. So now we have to apply m to that, right? So the definition of applying m to a vector is to write the matrix for m, which is ABCD, which I've written here, ABCD. You apply that to n of u. N of u is up here. It's this complicated thing. So I put n of u next to the matrix M, like that. Now there's some algebra. So we do the same thing, which is the horizontal line, vertical line mnemonic. So A times the first slot, A times PU1 plus QU2, that's this term, A times PU1 plus QU2. Add B times the second slot, B times RU1 plus SU2, that's what I've done here. So that gives us the first component. Now I have to take C times the first component, so C times PU1 plus QU2. It's this, C times PU1 plus QU2. And I add to that D times the second slot, so D times RU1 plus SU2. So there's a lot of terms, but it's the same rule as before, just applied to a complicated expression. Horizontal line, vertical line, multiply A times the first slot, B times the second slot, that goes here. C times the first slot, D times the second slot goes here. So once we have this, I'm just going to distribute and then collect like terms. So if I distribute A, there's APU1, AQU2, BRU1, BSU2, and I'm just going to factor out the U1s times that sum, and the U2s times this other sum. So I've distributed, again, if you want to be very explicit, this is APU1 plus AQU2 plus BRU1 plus BSU2, and on the bottom, CPU1 plus CQU2 plus DRU1 plus DSU2. So that's the distributing, and then I factor out the U1. So the U1 comes multiplied with AP and BR, APBR. The U2 comes multiplied with AQBS, AQBS. And on the bottom, U1 comes multiplied with CP plus DR, CPDR. And U2 comes multiplied with CQDS. CQDS, and there's a typo. This should be Q. CQDS, which is actually corrected on the next line. Good. CQDS. Here's the Q. So then the last step is, once we've factored and written out all of those terms, we go back to the definition of matrix times vector multiplication. So way back several slides ago, we decided that an arbitrary linear function applied to a vector, which has this output for an arbitrary input u1, u2, we will define that as a square matrix of 4 entries times the vector. So the only, I mean, this is just definition, going from here to here. The definition of a matrix. Okay, so some algebra, but what is the punchline? The punchline is that if I hand you any two linear functions, m and n, and I tell you the 4 numbers that determine those linear functions, and then you compose those linear functions by first applying n to u and then applying m to the result, you can always find a matrix which applied to the input gives you the same result in one step, and it happens to have these complicated products and sums inside the expression. Okay, that's the hardest part, so you should definitely ask questions now.
Doesn't seem, I mean, it's the hardest part, but it's not a hard part.
Exactly.
Okay, so you see the point, even if all of the algebra is a bit tedious. You see where I'm going?
Yeah.
Okay.
This is cool.
Good. Okay, so that's, by the way, the reason I included this slide to prove this is because in an algebra class you usually, or someone will usually stand in front of you and present this rule for how to multiply matrices. And they'll act as
Wait, seriously?
Yeah, usually day one. This is what happened in my freshman year with Trubilla, who is now retired. Day one of matrices in Algebra 2, he will stand in front of you and say, this is the rule for multiplying matrices, and he'll write down this last line with this complicated as fuck combination of products and sums, and just stand there with a straight face like this is completely natural, like you should just define this, and he'll just write this down and say, this is how you do it, and then he'll give you a worksheet, and you take the product of a bunch of matrices, and you have no idea, why should I multiply these and add them in this way? It's complete nonsense. And
It's like maybe maximum 10 minutes of presentation.
Yeah, I mean, it's just laziness, I think, to present the result without explaining, hey guys, these are composing functions, and if you want the functions to compose right, then you need to have the numbers add and multiply in this way. That's it. Sorry, I'm just bitter. Okay. Let's do some examples. So, I should say one more thing. So, the nice thing about the mnemonic I made you memorize a moment ago, which was that to multiply a matrix times a vector, like 1, 1, 0, 1 times 2, 1, right? You took the horizontal line and the vertical line and paired them. So this was 2 times 1 plus 1 times 1 is 3. And 0 times 2 plus 1 times 1, which is 1. This expression looks really complicated, but it's actually the same mnemonic, right? So 1, 1, 0, 1 times 1, 1, 0, 1. I'm just going to multiply the same matrix by itself twice. We take the horizontal line times the vertical line. 1 times 1 plus 1 times 0, right? So it's the same thing, but we just pretend the first part of the matrix is a vector. 1 times 1 plus 1 times 0 is 1. 1 times 1 plus 1 times 1 is 2. Then the second part, the bottom of the matrix, you just pretend each of these columns are vectors. So 0 times 1 plus 1 times 0 is 0. And then the fourth component is 0 times 1 plus 1 times 1 is 1. So although this rule looks very complicated, as it turns out, it's the same mnemonic as multiplying a matrix times a vector, but you just pretend each column of the second matrix is a separate vector, right? 1 times 1, 1 times 0, 1 times 1, 1 times 1, 0 times 1, 1 times 0, 0 times 1, 1 times 1. So this rule is not that complicated, is the punchline. Okay, that was a bit fast, but questions before I ask you to do this for some examples?
I do not have any questions. mnemonic seems quite simple.
Good. Okay. I think we're getting to the home stretch. Okay, so now I will ask you to do some matrix times matrix examples. So I've defined two matrices for you here. They look very simple. We will see in session 4 that these two matrices are associated with the spin of an electron along the x-axis and the z-axis, so they're quite important. They're called the Pauli matrices. And now I will ask you to multiply them. So the first one asks you to multiply sigma x, by the way, this is the Greek letter sigma, sigma x times sigma z, which I will copy for you here. Sigma z is 1, 0, 0, minus 1. So now you just need to apply that mnemonic I showed you to this product. What should I get in the top left?
Oh, the top left. I was just adding them up as I went.
Or give me all of them if you want, but whichever.
So on the top, I just had 0.
Good, so 0 times 1 plus 1 times 0 is 0. Good. Second part, top right.
Wait, what did I miss?
No, you got it right. The top left is 0 because it's 0.
I was saying that the whole thing all the way across is 0.
No. So the top right is 0 times 0 plus 1 times minus 1, right? So you have to match this horizontal line to this vertical line for the top right. Right? Because you treat each column of this matrix as a separate vector. So if I were multiplying this times this vector, it'd be 0 times 0 plus 1 times minus 1. You see? So the top right is minus 1.
Okay, the way I did this, I did 0 times 1 plus 0 times 0. I'm looking at the top horizontal of the left and the left vertical of the right.
Top horizontal and the left vertical. Okay, so this gives you the top left, right? So to find a position in the result, you take the horizontal part of the left matrix and the vertical part of the right matrix corresponding to the position you're interested in. So to get the top left, you take the top and the left, which is what you just told me. 0 times 1 plus 1 times 0. And that is indeed 0.
Okay.
But to get to
I was doing 0 times 0 plus 1 times 1.
Yeah, that's not what we want. So to get the top right,
Okay.
you take the top and the right. So 0 times 0 plus 1 times minus 1. Right.
So let me see. That would be 0 times 0 plus 1 times negative 1. So negative 1.
Good.
Okay.
Okay. So then bottom left, that should be the bottom and the left. So 1 times 1 is 0 times 0. So what do I get here?
1.
Good.
Wait, what?
So,
Okay.
oh my god, why did that all go away?
Oh, Jesus Christ.
Ah, it's back. Okay. I'm
Okay.
not very good at Epic Pen. So to get bottom left, we take bottom and left. That's the rule. So bottom and left. 1 times 1 plus 0 times 0, which is 1 for the bottom left. Good?
And then would the bottom right also be 0?
Yes.
Yeah, bottom right is
Okay.
bottom and right. 1 times 0 plus 0 times minus 1, which is
Okay, cool.
0. Good. That is the product of the Pauli matrices sigma x and sigma z. So in problem 3 of Matrices Challenge 1, you will take all products of these, which is actually quite important. The products of these are directly related to the uncertainty principle. So this is, in some sense, the most important application of matrices. So let's do one more. So sigma z, by the way, so here we multiplied sigma x times sigma z. Here we're going to multiply them in the other order, sigma z times sigma x. So the same two things multiplied in the other order. Usually, if you multiply two things in a different order, you get the same answer. X times y is y times x. So let's see if that actually happens. So sigma z is 1, 0, 0, minus 1. Sigma x is 0, 1, 1, 0. And we'll do the same mnemonic. So for the top left, we take the top and the left. So what do I get?
0.
Good. Top right, we take the top on the right.
1.
Good. Bottom left, bottom and left gives me what?
-1.
Good. And bottom right.
0.
Interesting.
As you said in the first slide, isn't this non-commutative?
It is indeed non-commutative, and now we see it directly. These two things are not the same.
But in a similar scenario, would it be a case where it looks like they just swapped places?
So you're asking, is it always the case that you can take the two off-diagonal elements and switch them, and then the results will be the same? Is that the question?
It would be interesting if it was that way.
It would be very interesting if that were true. It's not. It's almost never true. Good pattern recognition, though. Yeah, here the reason that it happens to be the case here is a happy accident, which is related to something called a Lie algebra. So, Lie algebra. By the way, this looks like the word lie, but it's pronounced Lie.
Algebra is lying to you.
Yes, the cake is a lie. I might give you a problem at this in the fourth one, but anyway, a Lie algebra is a different type of algebra. I mean, you studied the algebra of the real numbers in Algebra 1 and Algebra 2. A Lie algebra is a more interesting algebra, which involves matrices, and the reason that these two almost look the same except the components are swapped is a consequence of a result in Lie algebra, which I might explain, but it might take us a bit afield. So anyway, the punchline is that they are normally not swapped components like they happen to be here. Very good question, though. Other questions?
No. I have no more questions.
Good. Okay. I will try to wrap this up. Okay, so this is a rehash of what I just said. So as we saw on the previous slide, if you multiply two matrices and then multiply them in the other order, they are normally not the same. So we saw sigma x, sigma z is not the same as sigma z, sigma x. Opposite order will usually be different. Now, in my freshman Algebra 2 class with Tribilla, people acted like this was the fucking apocalypse. Like, you multiply two things in a different order and it's not the same, and people act like their heads are on fire because they're used to real numbers, right? You multiply real numbers in the opposite order, you get the same thing. But you should have expected this all along, because as I've been saying, matrix multiplication is function composition. A matrix is a function. You apply a matrix to a vector, it's a function applied to an input. And function composition usually does not commute. If you apply f of g of x, that's not the same as g of f of x. A simple example is if f of x is x squared and g of x is x plus 1, we can just try those two orders. F of g of x means to take the function g of x, which is x plus 1, and plug that in everywhere we see an x in f of x, which gives us x plus 1 quantity squared, which is x squared plus 2x plus 1. But if we go in the other order, g of f of x, that just means take f of x, which is x squared, and then plug that in everywhere you see an x in g of x, which gives you x squared plus 1. And obviously, x squared plus 2x plus 1 is not the same as x squared plus 1. So there's no magic here. I mean, it's just composing a function in a different order will give you a different answer, because that's how functions work. Matrices are just functions. So non-commutativity is extremely important. It's why these are useful in physics, but it's not magic. It's to be expected based on what you already know about functions.
So now I'm curious, are there inverse matrices?
Yeah, that is the topic of session 2, because functions are matrices. You know there are inverse functions. There should be inverse matrices. We will talk about that Monday.
Yes, I was going to ask if matrices had all of the different, how do I describe it? Details that functions do. Bad description.
Yeah, it's a very good and deep question. So there's a lot of properties of functions like inverses and images and pre-images. In a class on linear algebra, you would study all of those properties very deeply. So a function has an image, a matrix also has an image, and there's many theorems about the images of matrices. For instance, the pre-image of 0 for a function which is a matrix is called the kernel of the matrix. So you can study matrix type function properties like this. I don't know, I mean, if I'm trying to fit all of matrix theory into 4 sessions, I don't think I can talk about those. We will talk about inverses next time because that's absolutely essential. But the other stuff like images, pre-images, kernels, column space, null space, rank nullity theorem, we probably won't have time for unless I finish the 4 talks and there's like very high demand for more matrix talks.
We shall begin throwing death threats at you if you do not talk about them.
Good, I need more
Oh,
time.
I have another quick question. On the previous slide with special physics letter number 1 and its 2 subscripts,
Yes.
Sigma.
Sigma.
is the result also a 2 by 2?
Yes, the product of 2 by 2 matrices will always be 2 by 2.
So is it the case that multiplying 2 matrices will smaller one size?
Can you say that one more time because push to talk cut you off halfway through?
It's not even push to talk, it's just that Mason is doing. Okay. Is it the case that multiplying 2 matrices will result in a matrix that is of the same size as the smaller one?
Not always. So if the 2 matrices are both square, which means they have the same number of rows and columns, like this, 2 by 2 times 2 by 2, you will always get a 2 by 2. More generally, you could multiply, say, a 3 by 2. So this is maybe 3 by 2, and it's, I don't know, 1, 0, 0, 1, minus 1, 2. And you can multiply that by a matrix which is, say, 2 by 2. So maybe this thing is 2 by 2. 2 by 2, 1, I don't know, I'm making up numbers now. So this is going to be a 3 by 2 matrix. And here's the way I see that. So a 2 by 2 matrix maps a 2-dimensional vector into a 2-dimensional vector. So the input is 2-dimensional. The output is also 2-dimensional. That's the rule, that the input has dimension given by the right number, and the output has dimension given by the left number. So this has 2-dimensional input and 2-dimensional output. I compose that with a function that has 2-dimensional input and 3-dimensional output. So function composition tells me that I should take an input which is 2-dimensional, I get an output which is 2-dimensional, I feed that into another function whose input is 2-dimensional. Now the numbers match, right? Output 2-dimensional, input 2-dimensional, and my output is 3-dimensional. So I expect the product of these 2 matrices to be something whose output is 3-dimensional and whose input is 2-dimensional. So I get a 3 by 2 matrix. And the mnemonic is exactly the same. You do horizontal line, vertical line. So, I mean, I'll just multiply these. 1 times 1 plus 0 times 1 is 1. 1 times minus 1 is minus 1 plus 0 times 0. 0 times 1 is 0 plus 1 times 1 is 1. 0 times minus 1, 1 times 0 is 0. Minus 1 times 1 plus 2 times 1 is minus 1 plus 2, which is 1. Minus 1 times minus 1 is plus 1, plus 2 times 0 gives me a total of 1. So it's not always true that the product of 2 matrices will give the smaller the matrix, the smaller dimension, but it is true that the right dimension of the left matrix must match the left dimension of the right matrix, which is very hard to say. It sounds very complicated, but the reason is just function composition. The output of the first function has to be of the same shape as the input of the second function. That's all.
Alrighty then.
Yeah, good. I mean, this probably seems complicated, but we're focusing on 2 by 2 for now because it's simpler. So,
Unfortunately, I failed to get the two-dimensional input part and three-dimensional output. But the more that I think of it, it makes sense. Okay. Yeah.
okay, that's fine for now. We will, if we have time, we can talk more about non-square matrices like this later. For now, I want to focus on 2 by 2 because I want to do the simplest case and make sure you've mastered the simplest case and then generalize. Okay.
I am done with questions.
Good. Okay. A few more things. The last topic is commutators, and then we're finished. So I realize we're almost at 2 hours, but I mean, whatever. So, okay.
Actually, in a few seconds, we will pass 2 hours.
Well, I mean, we didn't start right at 6 p.m., so, I mean, I have a few minutes, but I don't care. So, right, again, matrices are functions, and we know how to add functions. If you add two functions, f and g, and apply that sum to a function, or sorry, to an input x, the definition is that that's the same as applying f to x and adding it to g of x, right? So since a matrix is a function, we can add two matrices as well. You can add a matrix M plus a matrix N times a vector U, or applied to a vector U, if you will, like this. So you might think, well, the most obvious thing for adding two matrices, I don't know, making up numbers again, the most obvious thing is to just add their elements. So maybe to add these, I should add the top left, which would give me 1 plus 0 is 1, 1 plus minus 1 is 0, 0 plus 0 is 0, and 1 plus 1 is 2. So you might think that's true, but you might have also thought that to multiply two matrices times, I don't know, 1, 0, 0, 1, you might have guessed that to multiply two matrices, you should just multiply each component, 1 times 1, 1 times 0, 1 times 0, and 1 times 1. But as we saw, that's definitely not true. You don't just pair each component and multiply them. There's something more complicated. You don't just multiply each one by its corresponding position in the other matrix. You have to do something more complicated with this mnemonic that involves horizontal lines and vertical lines. So to be completely careful, we should prove what the formula for adding two matrices is. Because if we're being careful, I mean, we don't want to make the mistake we would have made about multiplying matrices if we weren't being careful there. So in the next slide, I will prove for you how you add two matrices. As it turns out, we're being very careful for no good reason, because in this case, adding matrices just does the dumb thing you would have expected. And here's the proof. So two matrices. The matrix M is ABCD, the matrix N is PQRS, and the vector U is U1, U2. Now I will add the two matrices M plus N and apply that to the input U. So by the definition of function addition, that's M applied to the input U plus N applied to the input U. And then I've just written the two matrices for M and N. M applied to U and N applied to U. Then with our mnemonic, ABCD times U1, U2 is AU1 plus BU2. That's the horizontal vertical stuff. And then CU1 plus DU2. And then similarly, PQRS applied to U1, U2, PU1, QU2, RU1, SU2. Same thing. You add those two vectors, and then combine like terms. The things multiplying U1 are A and P, so A plus PU1, B plus QU2, C plus RU1, and D plus SU2. And then the last step is to write this thing as a matrix times a vector. And again, the usual rule is we picked the definition so that it is reminiscent of the positions of these 4 numbers. So to write this as a matrix times a vector, you take those 4 numbers and just put them in a square array. A plus P, B plus Q, C plus R. Wow, why did I write D plus 2?
I was about to say 2 is not equal to S.
Man, I make a lot of typos. I apologize. That should be D plus S. So D plus S in the bottom right times U1, U2. I mean, so this was kind of a complicated proof, just, I mean, keeping all these 8 numbers, A, B, C, D, P, Q, R, S, and doing the multiplication and summing. But at the end of the day, what we found is that the rule for adding matrices is way easier than the rule for multiplying matrices. Multiplying matrices required the horizontal line, vertical line mnemonic, but the rule for adding matrices is much easier. You just add the components. A plus P, A plus P. B plus Q, B plus Q. C plus R, C plus R. D plus S, D plus S. Just add the elements. Addition is much easier. But we should be careful. Question.
How did we go from step 2 to step 3?
Yeah, I wanted to question what happened to the multiplication or addition in the middle and how we turned that into a matrix.
So wait, do you mean from this step to this step, or from this step to this step?
It's always lagging behind the first one.
The first
you
one.
suggested.
Okay, so that one. And I've run out of undos. Okay, well, this one, I can simplify this because we know how to add 2 vectors. To add 2 vectors, you just add the components. So I will add the first vector to the second vector, which is AU1 plus...
But that's using what you're proving in itself.
No. I'm adding vectors, not adding matrices.
Yeah, he's...
I forgot that these are vectors.
Yeah, so
okay.
You should be careful. We've already defined vector addition, not matrix addition. They're different things, so we can use vector addition. Good objection, though. I mean.
Okay, that makes much more sense. Cool.
So, presumably the rest is pretty clear for this simplification.
Can I question for your last 2 steps there? You started with a vector, but you ended up with the matrix and a vector. How?
Yes, this was in this step. So we defined way back in the day, we defined a matrix ABCD times a vector U1, U2. We defined this to be AU1 plus BU2 and CU1 plus DU2. So this was a definition. There was no proof. This was just what we mean by writing this symbol next to this symbol. So we can always take a vector which is of this form on the right, and by definition re-express it as a matrix times a vector which is of this form on the left.
Oh, I see now.
Good.
Okay.
Yeah. So we've applied this. I mean, I've done a shitty thing by using the letter A twice, but you see what I'm doing, right? You substitute A with A plus P, right? So, yeah.
So you are in effect dividing by the vector U?
Kind of, yeah. We're kind of factorizing this vector into a vector times a matrix. So you can think of that as dividing out the vector if you want.
Does actual division ever come into play?
No. So you cannot divide by vectors in a usual vector space. You can impose an additional constraint on a vector space which requires that it admit division. And this gives you something called a division algebra, which is a more complicated structure. We can speak about that if you'd like, but it leads into the study of so-called quaternions and octonions, which are more complicated than vectors.
Is that like half dimensions?
No, those are fractals.
Okay, just checking.
Good, good. Very good questions on this slide, though. Objections to my steps are always welcomed because you should understand all of the steps in a proof. So, other thoughts on matrix addition before the last topic of commutators?
Nope.
I have no questions.
Okay, good. Last thing, and then I will leave you be. Okay, so now we know how to add matrices and also, by extension, how to subtract them. Because to subtract them, you just add -1 times the second one. So we will define a new operation called the commutator. So what is the commutator? The commutator takes two matrices, A and B, and we write it with this weird notation that has brackets. So you write left bracket A, comma B, right bracket. So this is just a compact notation for something called the commutator. And what I mean by this notation, A, comma B in brackets, is simply take the matrix A, multiply it by the matrix B using the matrix multiplication rules that we found before, and then subtract, since we know how to add and subtract matrices by the previous slide, you now subtract the matrix B times the matrix A. So all it is matrix multiplication and subtraction combined in a particular way. A times B minus B times A. Okay, it's not rocket science, but let me just make it very explicit. Why do we call it the commutator? Well, I told you that matrix multiplication is non-commutative. So A times B usually is not equal to B times A. So the commutator measures how much this equation fails to be true. A times B is not equal to B times A. What do I mean by measuring how much this equation fails? Well, if the commutator of two matrices is 0, so what do I mean? If the commutator AB, which is A times B minus B times A, if that is 0, well, now I can just add B times A to both sides of this equation, and I find AB equals BA. That means I can multiply the two matrices A and B in either order, A times B or B times A, and the result will be the same. That's usually not true, but sometimes it will be true. And if that's true, we say the matrices commute. So if the commutator is 0, A times B is the same as B times A, and the matrices commute. Usually not true, sometimes true. If the commutator is not 0, so A times B is not the same as B times A, then the matrices do not commute. That means AB minus BA is not equal to 0. So, I mean, again, it's not rocket science. This is, if you want to measure whether two things don't commute, you just take the difference of the products in different orders. And if it's 0, the order doesn't matter. And if it's non-zero, the order does matter. But I want to be very explicit about this object because it's quite central to quantum mechanics. So, questions about the commutator?
No.
I have no questions.
Okay, so this is clear to you?
Yes.
Yes.
Good. Okay. Now, so I will give you one example, and then after this I think there's a concluding slide and we're done. So, again, these polyspin matrices, I didn't tell you what sigma y is before, and I'm playing a small trick on you, because I've told you all of these are functions from R2 to R2. So now I'm just going to generalize without telling you to the complex numbers. This is now a function from C2 to C2. And again, if I had more time, I would do this properly, but instead I'm just going to put i's in so that these are complex numbers and trust that you believe me that we can just replace all of these elements by complex numbers and nothing would go wrong. But whatever. Okay, so we have to compute the commutator sigma x comma sigma y, which means we're going to commute sigma x with sigma y, which by definition is sigma x sigma y minus sigma y sigma x, and I will copy those for you and then ask you to do the matrix multiplication. So sigma x is 0, 1, 1, 0, sigma y is 0 minus I, 0, and then subtract the other order, 0 minus I I0, sigma x, 0, 1, 1, 0. Okay, so whoever is brave enough to volunteer, what is the matrix product for the first two?
I believe the top left is 1I or just I, right?
Yeah, so I, and then what's top right?
0,
0, bottom left,
0,
0, bottom right,
negative I,
minus I. Good. And second guy, so top left.
I'll do this side because Corbin did the other.
Good.
teamwork.
So it would seem that the top left side is going to be negative I.
Negative
I think
I.
that's right.
Top right.
Mason is doing stuff in the background.
Good, good. Minus I, then top right.
And the top right will be 0.
0, bottom left.
Bottom left is 0.
0, and bottom
Yeah.
right.
Bottom right is I.
I. Okay. And then we found that contrary to our expectations, to add or subtract matrices, you can just add or subtract the elements. So to subtract these two, what are the 4 components in order of the result?
So since Corbin isn't saying anything, speech, it'll be 2I, 0, 0, negative 2I.
Good, perfect. So that's the commutator of sigma x and sigma y, and you'll compute all 3 commutators of the xyz pairs of these guys on Matrices Challenge 1, which is the reason why you cannot simultaneously measure the spin of an electron in 2 different directions. It's the reason for the uncertainty principle is that these matrices do not commute. Their commutator is non-zero. Good, so that's exactly right. Last thing. So I'll do a quick proof for you. This is really just kind of silliness, but you might ask, if I commute 2 matrices, if I take the commutator and then take the commutator in the other order, what is the relationship between those 2 matrices? And the challenge is to prove that it's anti-symmetric. If you switch the order, you get a minus sign. So I could ask you to prove this, but I mean, it would almost be insulting your intelligence because the commutator of 2 matrices is A times B minus B times A. You could factor out a minus sign and then write this as B times A minus A times B, because distributing the minus sign would give you the minus BA, and minus minus is a plus AB. But by definition, this is the same as minus the commutator of B times A. So I will not even ask you to do that because it's just a couple of lines. Since the commutator has a minus sign in it, if you switch the order, you get an overall minus sign.
There's one slide left, so I'm still scared.
Good. Well, this is the concluding slide.
As written on.
There we go. Erased. Okay, so that's all of the content for the first meeting. So we've understood what a matrix is. It's a linear map in general from between 2 vector spaces, but in the examples we've considered between R2 and R2. So a matrix is a linear map which takes in a 2-dimensional vector and spits out another 2-dimensional vector. And since it's a function, we know how to compose those functions, and matrix multiplication is simply function composition. So that was what we learned really today. So we learned what we learned is, I guess, matrix equals function from R2 to R2, which is linear. So it has this important property we started with. And we learned that matrix multiplication has a complicated looking rule, but the rule was completely determined by our request, our imposition that it's the same as function composition. And now to conclude, a teaser for the remaining units on matrices. Since now we've introduced the commutator, so one more thing we learned is that the product AB is not always the same as the product BA. So a teaser for the remaining units. This thing we've just learned about, the commutator, as I've hinted at repeatedly, appears in the uncertainty principle. So we will see in Matrices session 4 that in quantum mechanics, the theory of quantum physics, anything you can measure, so anything in the lab you could go in and measure with apparatus, will be associated with a matrix. So every measurable comes along with a matrix. So measurables are matrices, and the current state of the system you're studying is represented by a vector. So if I prepare my electron to be in a particular state, that state can be written down as a vector, a two-column vector, or sorry, a two-component vector like AB. So that's the state. And then the thing I'm going to measure is a matrix. So my measurable will be some matrix ABCD. So there's a general fact, which I'll tell you more about later. And the fact is, if A and B are two measurables, so these are two things I can measure, which means A and B both come along with matrices, so A and B are associated with matrices. So suppose A and B are two measurables, therefore matrices, and we're in a state associated with a vector u. Then if we write down two numbers, delta sub A, this is the capital Greek letter delta, delta sub A, and delta sub B for the uncertainties in those two measurements. That means if I measure the thing associated with A, there's going to be some error in my measurement. That's delta A. Delta A is just a number.
Hold up, something just got muted for.
Oh,
What did he say?
he said, hold up, something just got muted, but I don't know what that means.
Test.
I heard that. Can you hear me?
I'm gonna reconnect.
Okay.
Isn't delta the difference?
Often in math, delta is used for a difference of two quantities. Here we're using it for an uncertainty, which is
Test.
testicle.
Test.
You guys are talking, but I can't hear you. What is this?
No, why can't you hear us?
Let me message.
I already did that. I'll try it again. Blue.
Woo.
That worked.
You can hear
I have
us?
no idea what happened there.
Weird.
I'll continue.
Yes, okay. So we were talking about quantum mechanics. So in quantum mechanics, if I can measure something, it's a matrix. If it's a state of my system, it's a vector. And then we have two numbers which are called uncertainties. Those are just real numbers. That could be like 5 or 10. The uncertainty just tells you, if you measure something, how big is the error. So a bigger error means you measure something and you could be way wrong. A smaller uncertainty means you measure something and it will be very precise, right? So those are delta A and delta B. So here's the statement. A and B are two measurables, which means they're associated with matrices. We are in a state U that tells me how my system is prepared. And then we have two uncertainties, delta A and delta B, which tell me the error in my measurement for the two measurables associated with A and B. Then here is the statement of the uncertainty principle. if I multiply those two errors, delta A times delta B, that product must be bigger than or equal to this expression, which involves the vector u and the commutator of those two matrices A and B. So this is a bit of a tease, because I haven't told you what this symbol means. This is read as dagger. This is read in LaTeX. It's dagger. It looks like a dagger. So I haven't told you.
I was
what
gonna
dagger
say.
is. It looks very violent, but I haven't told you what dagger is yet, and I will in meeting 4. But already after the first session, you can tell that since there's a commutator inside this expression, and the bars are just absolute values, those are, I mean, you know what an absolute value is. If the commutator is larger, so if these matrices fail to commute, then my uncertainties are bigger. So the more my matrices don't commute, the larger the error in my measurement will be. And this is the core of the uncertainty principle. When matrices don't commute, you cannot get an accurate measurement of the measurables associated with those matrices. That's it. In one line, that's the uncertainty principle. There's no magic. It's just when matrices don't commute, you can't get an accurate measurement. And I'll try to make that more precise and tell you more about it as we go on.
Wonderful.
Good. Okay. Long meeting, but I think we covered a lot of ground. Comments, thoughts, feedback for me, any ideas for the next couple meetings? What do you think?
I have no comments or thoughts. I'd be happy with